Welcome to the TWIML AI Podcast. I'm your host, Sam Charrington. All right, everyone. I am on the line with Matteo Chinazzi. Matteo is an associate research scientist at Northeastern University. Matteo, welcome to the TWIML AI Podcast.
Hi, Sam. Thank you for having me. It's great to be part of this show.
Thank you. I'm looking forward to jumping into our conversation about some work that you've done recently to apply machine learning, in particular word embeddings and word2vec, to the physics research space. In fact, we've covered similar applications. Most recently, the TWIML AI Podcast number 291 took a look at some applications of machine learning to identify new materials by looking at materials research publications. But very interested in learning a little bit more about your application. But before we do that, tell us a little bit about your background and how you came to work on kind of physics and machine learning. And you're also doing some work in computational epidemiology as well, if I understand correctly.
Yeah, correct. So actually, my background is a bit strange in a sense because my formal background is actually in economics. So I hold a PhD in economics from Sant'Anna University in Italy. But actually, during my career path, I've always worked, the intersection between, economics, physics, and computer science in a sense, because I'm always being involved in this kind of field of research, which is called complex systems and applied network science, typically. And so what I've been working lately actually are essentially two main kind of broad area of research. One is, as you mentioned now, computational epidemiology, which means this idea of actually building these large-scale simulators that can allow us to kind of model the spread of a disease at the global scale. So you can imagine essentially what we are doing at our lab is kind of have this essentially complex piece of software that is able to kind of simulate in a realistic manner the evolution of an epidemic at a global scale. So imagine, let's say, having Zika starting at a given point in Brazil and then spreading around the world, or having, for example, to try to model, let's say, the patterns of the seasonal flu or a pandemic flu, let's say, in the United States. So this is the kind of research we are doing. And on the other hand, the other, let's say, focus of my research was actually to work on a discipline which is called science of science. And the idea there is essentially to kind of look under a microscope of how science works, meaning, for example, how it evolves over time, how collaborations occurs between different scientists and between different fields, how scientists pick their research problems, how they, for example, move across different institutions, how nations develop expertise in different fields of research, and so on. So those are kind of my main two topics of research at the moment.
How did you get started, in particular on that science of science? What led you to start exploring that area in your research?
Well, actually, that kind of comes in a sense from my economic background, because the reason why I was attracted to economics in the first place was this idea of actually trying to understand, in a sense, human behavior and all the interactions that occurs between individuals. And so translating that to science of science, the idea is that, okay, you have all these many people working on producing new and innovative research. You're trying to understand how you can, for example, accelerate science and, let's say, redirect funding so you can get, let's say, the most out of it, and you can maybe, let's say, promote a specific set of expertise in specific institutions or places in the world. So how will you do that? And one way in which I approached the problem was actually to first try to understand how you can actually map a research space in a given field. In our case, we started actually looking at physics as our, let's say, baseline, if you wish, because, the people with whom I'm working most of the time are actually people trained in physics or computer science. So that was kind of the natural way to go in a sense.
Well, let's dig into this research. So you start with the goal of mapping the physics community via the research. Did you define it more specifically than that, or did you set out broadly to see what you could see by applying machine learning to the space?
No, actually, we're using kind of a precise definition, given that this kind of due to the kind of data we are using. So in our case, we're using publications from the American Physical Society. So essentially, we have a data set with all the publications and all the papers that were published in the journals of the American Physical Society, and we use that as our corpus in a sense. And the reason why we started looking at this is because there is, let's say, a very specific classification that allows you to kind of look at each paper and know if that paper, which kind of topics are covered in that specific paper, given that they have this classification that with different essentially codes that tells you, okay, this paper is about nuclear physics and specifically this subtopic of nuclear physics versus astrophysics or something different. And so the fact that we were able to kind of map simultaneously publications, authors, locations through the affiliations of the authors and topics, research topics, that's kind of what we needed to be able to generate and then infer this knowledge and research space in physics.
The technique that you applied is Word2Vec specifically, or word embeddings more generally?
Word embeddings, in a sense that the model that we're actually using is StarSpace, which was developed by Facebook Research AI Group. But is one of, let's say, of the many, in a sense, variations of the Word2Vec approach. So the idea in our case is that we are treating each author as a bag of topics, so as a bag of research fields in which that author has worked. And then we use this bag of topics to kind of infer the embeddings for each specific research sub-area, in a sense, and create then this mapping of the overall knowledge space by essentially looking at the expertise of authors to guide us on what it means for two topics to be similar to each other. So that's the general idea. So, for example, if we go back to the Word2Vec idea there, the main assumption is to use this distributional hypothesis idea, then the fact that essentially you can infer the meaning of a word by looking at the context of that word. And in our case, let's say the analogy in our case is that we are saying, okay, we actually observe the publication record of scientists. So we know what each scientist is able to actually produce in terms of research. And so we use that as our, let's say, way to infer what is the context of a specific subtopic. And so we're saying, okay, given that this author has published, for example, in nuclear physics, we can look at what other topics that author has published on, and we use that as a context to kind of predict the embedding for the former, for example.
Okay. In that sense, does it mean that the approach that you've taken is more of a supervised type of an approach, using the labels that were available in the journals for the different research than Word2Vec, or would you still consider it, unsupervised or semi-supervised or something like that?
So yeah, actually, it can be considered, if you wish, supervised learning in a sense that we do have the codes. So we do have these PACS codes, that stands for Physics and Astronomy Classification Scheme, that are attached to each paper.
Okay.
But actually, the way in which we use them, they are as if they were simple keywords, in a sense that we are not trying to actually, for example, create an embedding of the author, given the labels that we have associated to that author. We are actually treating each bag of labels, in a sense, as a standalone document. So, for example, the idea is that our idea actually is that you can apply this approach in general to any kind of keyword list that you have associated to papers, which can be even inferred, for example, semi-automatically from titles or abstracts of papers. But the reason why we chose to use this specific dataset with this specific taxonomy already embedded into it was because this will give us a way to actually have a ground truth, a baseline to compare our results with. So the idea is that we know that this taxonomy exists. We know that we have these hierarchical schemes that tells us that physics is divided, for example, in 10 big sections, and then each section has many different subfields and so on. But we're not using that kind of information at training time. So the idea is that once we have our embeddings, can we actually see that same, in a sense, classification scheme exposed? So can we use that to actually validate what we are going to observe? Mm-hmm. And that's why we're using it in that sense.
Got it. Are you also using the full text of the research papers, or are you only using these keywords as kind of your document?
No, we are only using these keywords because really our idea was to kind of just, in a sense, start with a minimal level of information we could get, in a sense. Okay. But yes, really, our goal actually is try to kind of extend it up beyond physics, actually, where we do not have, in a sense, a classification scheme. And then at that point, yes, we will go towards the direction of using, for example, text of abstracts or titles to actually infer automatically, in a sense, these keywords.
Okay. And so with that as the backdrop, what are some of the things that you've been able to kind of identify within this embedding space that you were able to create?
Yeah, so what we were able to do essentially was to kind of fingerprint the scientific production of cities and recover what is, let's say, an effect that is already observed in literature using different approaches, which is this idea of this so-called principle of relatedness. And that has to do
Principle of
with
relatedness?
Yes, that's
Okay.
correct. And so that's something that comes, let's say, from the economic geography literature in the first place. And that's the idea, for example, that if you look, let's say, at the production and exports of a nation, so of a country, and you look, let's say, what kind of product categories they export to their trade partners, you can kind of predict what new categories they are going to be able to export next by first getting a measure of the relatedness between the different product categories, and then by essentially kind of checking where is the overall production, the overall level of expertise of a country, and then use that to kind of predict what is the next item you're going to export. And the idea there is that if you're working in a part of, let's say, this product space in which you have, let's say, you have skills and expertise in different product categories, and you have a way to measure relatedness with another product category that will help you kind of predict if that's where you're going to go next or not. And in our case, essentially, this kind of the analogy in our case is that now at this point we're looking at cities. So we kind of collect all the publications at the geographical level. And then we use our knowledge space, our research space built using the embeddings to measure this level of relatedness and then kind of predict where each city will go next in terms of their scientific expertise. So, for example, we might look at the publication records in a specific time window, let's say from 2000 to 2003. Then we're going to kind of predict using this embedding space whether or not the specific city will have a so-called revealed comparative advantage in a specific subfield in physics in the next time window, for example.
And presumably you were able to identify those kinds of trends with the embedding space you created?
Yes, that's correct.
What are some examples of, do any examples of cities and research topics come to mind?
Yeah, so what we do essentially is like on one hand, what we do is, for example, look at specific cities and look like at how their activities cluster in this embedded space. And so, for example, as we show in the paper, we can, let's say, see that cities like Brussels, for example, they have a clear level of expertise and expert knowledge in nuclear physics, for example, while you might have, let's say, other cities like Grenoble that instead specialize more on condensed matter physics. So this is what you can actually really visually observe by just using this embedding space and using a network to kind of represent the interactions between these different vectors representing the topics. And then what we show is that indeed we can then use this model to kind of rank the probability of a given city to enter in a specific field, and then use that, if you want, as your classifier that will tell you with a yes or no whether or not that activity is going to be developed at the next time step. And for that, we kind of show that, let's say, distribution of our predictions is actually better than a simple random model where, let's say, all this expertise will evolve randomly.
And so is the model primarily good at identifying new research topics that are closely adjacent to existing research topics as a direction for a given city? Or is there some ability to take more leaps, if you will?
So that's actually one of the things that are studied in the literature. And the idea is that when you build this space, you compute a so-called measure of knowledge density, in a sense. So imagine that now you have this in our case, very complex n-dimensional space where you have different research topics, so different points placed in this n-dimensional space, and you want to look if there is any specific area of this space where a specific entity, in our case, let's say a city, has a high density of topics that are active. Okay, so what you show is that actually that city is more, let's say, likely to be actually able to develop an expertise around that area. So in areas in which the density of points is high, and that is also what is found in the literature using essentially also different techniques, and that is like a pretty robust result. The only, let's say, exception to that is that, for example, in the case I think that was of economic activities, what they show is that if you are, for example, a country that is an intermediate level of development, you have more chances of actually jump to a different part of the space, in a sense, And there might be ways for you to kind of optimize your trajectory in this space precisely by kind of knowing what is the map around you and knowing where you have your level of expertise.
You mentioned earlier that you used an algorithm that was developed at Facebook. What was that algorithm?
The name is Starspace.
Starspace?
Yes.
And can you go into a little bit more detail? How does it differ from Word2Vec?
Yeah, sure. So the main difference that here we actually don't have a neural network. So the embeddings are not trained as in Word2Vec as like a hidden layer in a very simple neural network. But in this case, instead, you kind of directly treat the problem as an optimization problem. So you have this matrix that represents essentially your dictionary. So in our case, let's say all the different research topics that we have in our papers. And then the other dimension will be the actual embedding dimension that you picked. And then you have a loss function that kind of tries to optimize essentially this and create these embeddings and optimize this matrix by essentially allowing you to play with essentially what is to be considered similar to each other. So essentially the way in which the loss function is written is that you have a generator of positive and negative pairs, which will change depending on the kind of problem that you're trying to address. So for example, in our case, let's say we have a list of topics for a researcher. So the positive pairs will be, for example, the fact that I leave one of these topics out, and that will be my target. So what I actually want to kind of predict. And then all the other topics within that bag will actually be something that I can use to generate these positive pairs. So these pairs that you'll have, in our case, for example, a very high cosine similarity. And then on the other side, you have a negative pair generator, which instead kind of throws randomly other topics from, for example, other bag of topics or your actual dictionary. And those are the ones in which you kind of want to stay away from, in a sense. And that is done in a similar way as it is done also in some implementation Word2Vec using negative sampling, meaning that you indeed sample randomly what are, let's say, the negative cases, so that the points in the space from which you want to be far, in a sense. And so all of this essentially is treated as just an optimization problem, which tries to directly learn this matrix.
So do you think that a neural network-based approach would get you different results in any significant way? Is that something that you're interested in, or not so much?
No, actually, I think they will probably give different results in a sense that what we are not playing with right now is actually this idea of having, in a sense, a time spent list of topics. Like let's say when you use, let's say, Word2Vec in a Word, the idea is that you have, for example, this kind of rolling window that defines your context, right? So you can say, okay, look at 2 words before or afterwards. And then depending on whether you're using the continuous bag of words or the skip gram approach, one is the target or the other. But I mean, essentially the idea is that you have this kind of rolling window in your sentence that picks up what is the context. Well, in our case, what we are doing is that we are treating everything as if all the production of a given scientist is the context. And there is no idea of, in a sense, temporal distance embedded yet. So one idea would be to maybe try to apply this algorithm, maybe using a word, even just using a continuous bag of word implementation of Word2Vec, for example, to adapt this idea of having a rolling window. Mm-hmm. And the other thing is that, for example, instead if we were to use Word2Vec in the skip gram approach, then actually will give us something probably maybe that might be different than what we're observing right now. So, of course, let's say in the paper, what they show is that actually this method seems to have better results in the use cases they test than, for example, fast text, Word2Vec, and I think also Glove, as far as I remember. But yes, it's definitely something we are willing to explore. So our idea is indeed actually not to try to kind of come up with what will be the best way of creating these embeddings, given that we have a very specific problem in mind. So we are not aiming at creating embeddings that should work for, let's say, whatever task at hand, but actually that should work for to test very specific ideas, in a sense.
Are you incorporating in any way some kind of weighting of a given researcher's volume of work or significance of work in a given area, or is their kind of bag of topics just based on anything that they've been active in?
No, actually, it's based on anything they've been active in, and that's actually by design, and that's something we wanted to do. We wanted to do like that, and the reason for that is that let's say the other approaches that do not use embeddings to kind of address the same problem have that kind of filtering. So have this idea of actually first filtering, for example, what are the topics in which a nation or an institution or an entity have what is called a reveal comparative advantage. So which, putting in your words, would be something like, okay, identify where that scientist is most active on. So remove, for example, all the side papers that have topics that come out maybe of side projects or fields he abandoned or something like that. Well, in our case, we want to say, no, we actually don't want to embed any of that information in our embedding. So we want to try to say, okay, what if we are blind? We just keep and get a big pile of papers from an author. We just list all the topics in which he has worked on and train on that. So we don't further filtering without trying to kind of tweak the data to get the best result possible. Our idea was precisely to show that you don't need to do that to have the same results that you have with a lot of these manual, let's say, checks and optimizations.
Given that you're focused on a very specific task, what was your performance metric against that task?
So, okay, there are different, in a sense, checks and validations we did. So the first validation, which was not in a sense quantified, but was just in a sense a visual inspection, was what I was telling you before of actually comparing our results from this PACS classification scheme. So the idea is that what we did was that we obtained these embeddings, then we used them to create actually a research network space. And the idea there is that we are borrowing, let's say, techniques and tools from network science. And at that point, what we're doing is that we are treating each topic as a node in a network, where the nodes are connected to each other through edges, and each edge as a weight has actually the amount of similarity, relatedness that those two topics share, which in our case would simply be the cosine similarity of two topics. Then after building this network, we kind of use what are called like spring layouts in this kind of literature, which essentially the basic idea is that imagine that you have these balls into space that are representing your different topics, and you have these different edges connecting them. Now imagine those edges are actually springs that have different force depending on the level of similarities of those nodes, so those entities. And so the stronger the similarity, the closer those nodes will be in your visual representation. And so we use that to build essentially this research network space. And as in a sense, as our way to kind of make the projection from the embedding space to a 2D dimensional plot in a sense. And by doing that, we can kind of clearly identify the 10 macro areas in which we know that PACS classification divides the different branches of physics. And that was kind of our first, in a sense, validation after running the embedding problem, because we knew that we weren't providing that kind of information to the algorithm. So we know that that kind of information of the existence of this hierarchical classification of topics was not used at training time. So that was our first way to benchmark ourselves and say, okay, look, actually our results indeed look promising. And the second way in which we tested was actually to indeed measure the predictive power of the algorithm. And at that point, what we did was essentially to look at each city at a given point in time, so in a given time window, list the topics in which that city had a comparative advantage. So list the topics in which, the research topics in which that city was particularly good at producing new research. And then try to predict what will happen next as if it was, let's say, a classifier problem where you have 1 if you're going to develop in that new field and 0 otherwise. And then use a standard metric like a ROC curve or something like that to actually kind of get a sense if our model was better than a random model when instead this evolution of expertise was occurring randomly. So those are the two ways in which we tested our results.
And did you have any external comparisons available to you? In the first of those two cases, you're kind of comparing against common sense, but you've mentioned previous research on the economic side, for example. Are the results compatible such that you can kind of compare what you're seeing to what previous papers have shown?
Yes. So, for example, in terms of the kind of, in a sense, so let's say the map of the knowledge space that we find in physics is actually very similar to the maps that are obtained, for example, by other researchers using different techniques, for example, looking at citation networks. So how different subfields cite each other. And yes, actually, what we have found is that our results are well in line with what has been found using other methodologies and other approaches, in actually even other data sets, as far as I remember. And so that was, let's say, confirmed in a sense. So on the physics side, on the, let's say, more, let's say, theoretical side of whether or not we could like reproduce this principle of relatedness effect, indeed, also in that case, we are getting results that are well in line with what has been found in the literature.
Where do you see this going? What's next in this line of inquiry for you, and what do you think it opens up?
Well, first of all, our idea is to actually extend this, and this is something we're already doing, to other things rather than physics. So, for example, now there is, let's say, a lot of data available to researchers in this field, like, for example, Google Scholar, Microsoft Academic Graph, and other big databases that could allow you to actually extend this approach in a sense at scale, look at different disciplines. And then we're already working on that. We already have some preliminary results on that. And for example, what we have seen is that by using the same approach in the Microsoft Academic Graph, which is essentially another of these bibliometric data sets that kind of include at that point all the different fields in science. And for example, using it there, we kind of can replicate fully the results we get in physics to actually all the other fields. But then actually our goal is to start using this embedding space as our, let's say, additional tool in our toolkit to actually try to do something new. So for example, all these papers that, let's say, for example, track the evolution of the semantics of a term over time, for example. So you can imagine that given that we have this space in which we can embed topics, but potentially also authors, fields, and so on, we can kind of try to understand, for example, how authors move in this space. Or, for example, can we find the same kind of analogies that you have in the classic, let's say, examples of king, queen, man, woman, and so on, arithmetics? Can we do the same in science, for example? So can we kind of understand where there might be gaps into science by actually try to play with these analogies? So try to see, for example, what happens if you use or if you apply a specific subfield in computer science to maybe a field in which that was never considered as a kind of technique. So once, let's say, you get a sense of how to navigate this space, then you can try all these kind of scenarios and thought experiments that maybe can give you more of an intuition of how science really works underneath. So what is the actual structure of the knowledge that is like kind of keeping everything together?
It strikes me that it's possible that the shifts that we see in research have less to do with changes happening, in, new research in a city, and more to do with changes in the way we describe our research and these tags that we apply to them. And I'm wondering if you've explored that at all.
No, in a sense the way I think I understand your point is not a problem for us. So the way in which we define strength, in a sense, of a city in a specific topic is by using this concept borrowed from economics of revealed comparative advantage, which put in a very simple terms is like saying, okay, that your podcast, for example, if you compare it to other shows, has a comparative advantage, let's say, in machine learning, simply because the share of time that you devote to this topic compared to all the other possible topics that you might consider is larger than the average share of podcasts that talk about machine learning. Mm-hmm. So it's a relative measure. So it's like saying, okay, imagine, for example, now from T to T+1, you have an explosion of papers using Word2Vec, for example. So let's say that your share of Word2Vec papers goes from 5% of the publications to 10%. Mm-hmm. Okay. That's not really going to affect the results, because what we're going to look is what is your own, as a country, as a city, share of publication in that topic compared to what the world is doing. So for example, if at time T you had 10% of your publications that were in Word2Vec in the world was 5%, then you kind of have a value of this revealed comparative advantage that is 2, which means that you are above average on how much you're publishing in that topic. If at the next time step, let's say, for example, Word2Vec publications increase, your share of publication doesn't change. So you still have that actually your share of publications in Word2Vec papers is 10%, but now the word share is 10% as well, then your kind of strength have decreased. So the effect of controlling for the actual absolute size of a different topics or a different field is embedded in our definition of how we define, in a sense, strength and weakness in different, or expertise in different fields of research. So what we observe is actually indeed a relative measure of how good you are with respect to all the other players in the arena, in a sense.
I think the scenario I was trying to point out, and this may be way in the weeds and not at all irrelevant, but what I was trying to get at is, what if we have this machine learning podcast and we talk about, embeddings all the time, and then the term word to vec suddenly becomes more popular, and so we start using that as opposed to, another way of describing the same thing, or, the field matures and we get more and more specific. Your approach, kind of out of necessity, is really concerned with, the way we're describing what we're doing and what we can learn about the way we describe what we're doing, as opposed to, what we're actually doing. That your research isn't really involved in kind of mapping that to the cities themselves and trying to, project, for example, economic value that comes out of any of these changes in research areas to validate the model in any way?
Two things actually. So in terms of, let's say, as you said, maybe we get more specific in like talking on, let's say, discussing about specific topics. So we might kind of switch the way in which discuss that. That's actually the whole reason why we introduced the embedding idea, the embedding model around this problem. Mm-hmm. Precisely because if your embedding works well, then that kind of transition shouldn't really matter. Because, for example, if now you start from talking, from word to back to, let's say, using only Glove, in theory, your, let's say, system, so your, let's say, knowledge space should have already accounted for that. So it should have already placed, for example, the two vectors very close to each other. So right. I don't think that's actually a problem given how we are setting up the whole system, which is kind of why we decided to go with the embedding approach rather than, for example, do probability counts or occurrence counts as others authors have been doing, precisely because of the problem you're saying.
Okay.
And regarding the economic impact, actually, indeed, that's actually the next step in a sense, and that's actually why we want to kind of extend our approach to different areas. For example, because another thing that we have been working on, and actually you can imagine doing, is that you don't only have academic publications in the world, but for example, you also have patents. So you actually also have recordings of what, for example, cities, if we want to stick with the geographical dimension, what cities have been publishing, both in terms, for example, of technology, so of patent applications, and also publications. And so you can imagine that if you actually are able to build this big knowledge space that includes not only knowledge as publications, but actually, for example, technology, then maybe you're actually able to kind of draw a line between the expertise that you might be developing in a specific field, research-wise, and the kind of maybe patenting activity that it might open up for you in the future. Okay. And then the actual link between the patenting activity and the actual economic value, I would say, is pretty straightforward. I mean, it's still a lot of work to do, but I mean, it's something that anyway can be done. So that's actually the reason why we are kind of trying to refine this approach, precisely because once you have this space that can tell you essentially how science works and how technology works as an extension, depending if you put also the patent applications in or not, then you're actually able to answer those kind of questions.
Fantastic. Matteo, thanks so much for taking the time to chat with us about what you're up to.
Thank you for having me.
All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.